Hi, welcome to our channel of IGNOU audiobooks, Indira Gandhi National Open University, School of Sciences, SOS, Master's Degree Programs, M.Sc, Chemistry, MSCHEM, First Year, MCH, 012 Stereochemistry and Reactive Intermediates, Block-1 Stereochemistry-I, Unit-2 Stereoisomerism of Molecules with Chiral Centers, 2.1 Introduction. In the first unit of this course, we recapitulated some concepts that you have read in your undergraduate classes. These were related to the classification of stereoisomerism and the concept of optical activity. We discussed various ways of structural representation of three-dimensional molecules in two dimensions as it becomes necessary to explain the stereochemistry of that molecule. You also learned the interconversion of one type of projection into another. It was learnt that a carbon atom with four different groups is called a chiral carbon, and a molecule containing such a carbon atom has a non-superimposable mirror image. The two isomers are called enantiomers. We discussed the types of symmetry elements and their role in explaining the existence of enantiomerism and optical activity of organic molecules. In the second unit, we would explain stereoisomerism in the molecules with 1, 2, 3 or more chiral centers. You would learn the process of racemization and separation of two isomers from a racemic mixture. This would be followed by the concept of optical purity. In the first unit you have read that stereoisomers are mainly of two types, viz., the configurational and conformational isomers. The next unit deals with conformational isomerism and conformational isomers. Expected learning outcomes. After studying this unit, you should be able to explain the stereoisomerism in molecules with 1, 2, 3 or more chiral centers, define and differentiate among the enantiomers, diastereomers and mesocompounds, define racemic mixtures and explain their formation and properties. List and describe the methods of separating racemic mixtures, identify a pseudo-asymmetric center, and explain the criteria of optical purity in the context of optical isomers. 2.2 Molecules with one chiral center. In the previous unit, we have discussed about asymmetry and chirality. You would recall that asymmetric carbon atom has four different groups attached to it. If one such carbon atom is present in a molecule, then the molecule becomes chiral, and this carbon atom is called a chiral center. Due to this, stereoisomerism is generated in the molecule, hence it is also called the stereogenic center. However, it is not correct to use the term chiral carbon atom because it is the overall molecule which is chiral. The term chiral carbon is sometimes used when we have to differentiate this carbon atom from other atoms like nitrogen or phosphorus, etc. Present in a molecule. Let us now apply the concept of chirality to a simple molecule like methane, with four hydrogen atoms tetrahedrally attached to a carbon atom. You will be able to visualize that the molecule of methane and its mirror image would be superimposable, Fig. 2.1a. We find the similar situation in case of bromomethane, Figure 2.1b, and bromochloromethane, Fig. 2.1c. These molecules are achiral and do not show optical isomerism. Let us consider the molecule of bromochloroiodimethane. Here we would observe that this molecule and its mirror image are not identical, as these are non-superimposable mirror images, Figure 2.1d, hence this is a chiral molecule. The two mirror images in D differ only in the arrangement of atoms in space, that is, in their spatial arrangement. In other words, these possess different configuration. This molecule has one carbon atom, which is attached to four different groups, whereas in case of methane, bromomethane and bromochloromethane, all the four groups are not different. Figure 2.1, non-chiral molecules, A, methane, B, bromomethane, C, bromochloromethane, chiral molecule, D, bromochloroiodimethane. We have already studied that if a molecule contains one asymmetric carbon atom, then it gives rise to a pair of isomers called enantiomers. Both of these isomers are optically active and rotate the plane polarized light in opposite direction with the same magnitude. The isomer which rotates the plane polarized light towards right side is called dextrorotatory and is represented by a sign or prefixed by the letter D before its name. Similarly, the isomer which rotates the plane polarized towards left side is called levorotatory and is represented by a sign or prefixed by the letter L before its name. Lactic acid was the first compound which was studied in connection with optical isomerism. It contains one asymmetric carbon atom and so it exhibits optical activity. The enantiomers of lactic acid and the non-superimposable molecule are shown in Figure 2.2. Figure 2.2, enantiomers and the non-superimposable molecule of L-lactic acid. In lactic acid, the central carbon atom is attached to 4 different substituents, viz. H, CH3, OH and COOH, which are arranged tetrahedrally around the carbon. These isomers, being non-superimposable mirror images of each other, hence are called enantiomers. It should be noted that this molecule as a whole is chiral rather than possessing one chiral carbon atom. It has been suggested that it is more appropriate to call carbon atom of this type a stereogenic center, as mentioned earlier. Also, according to epoch rules, the term chiral center is used for stereochemical notation. The enantiomers of Butan-2 all are represented as shown in Figure 2.3. It can be seen that the two are non-superimposable. Figure 2.3, enantiomers and the non-superimposable molecule of Butan-2 all. Some more examples of compounds containing one asymmetric carbon atom are given in Figure 2.4. It should be noted that usually the asymmetric carbon atom or the chiral center is shown by an asterisk mark. Molecules containing a single chiral center are always chiral and lead to a pair of enantiomers. A carbon atom forming a double bond cannot be a chiral center since it cannot have 4 different substituents. Figure 2.4, molecules with one stereogenic center. You know from your previous classes that the absolute configuration of enantiomers is designated by the letters R and S. You would recall that, for assigning the configuration for groups attached to the asymmetric carbon atom are given the priorities according to CIP rules. The molecule is viewed from a direction that is opposite to the group getting the 4th priority. If the sequence of other 3 groups from 1 to 3 is clockwise, then it is assigned a configuration, and if the sequence is anticlockwise, then it is assigned S configuration. For example, the 2 enantiomers of lactic acid are shown in Figure 2.5, where the priorities to different substituents are depicted along with the configuration of each enantiomer. Figure 2.5, absolute configuration of enantiomers of lactic acid. In the next section, we will discuss the molecules containing 2 chiral centers. 2.3 Molecules with 2 chiral centers. The stereoisomers with 2 chiral centers exist not only in the form of enantiomers as observed in molecules with 1 chiral center, but also show another type of stereoisomers called the diastereoisomers. You have prior knowledge regarding the later type also. We would recall and discuss these 2 in this subsection. These stereoisomers broadly fall into 2 categories. These are isomers with dissimilar stereogenic centers, isomers with similar stereogenic centers. How do we find out the number of isomers in these? In the following subsection, we would understand the way stereoisomers are identified in these molecules and study the stereoisomerism in case of molecules with dissimilar stereogenic centers. 2.3.1 Enantiomers and diastereoisomers. Dissimilar stereogenic centers. There is a general rule by which the number of stereoisomers which can be shown by a molecule with 2 or more stereogenic centers can be determined. According to it, in compounds where the stereoisomerism is due to chiral centers, the total number of stereoisomers will not exceed 2n, where n is equal to the number of chiral centers. Let us understand it with the help of an example. These 2,3-dibromopentane As can be seen by a two-dimensional bond line structure, this molecule contains two asymmetric carbon atoms. Therefore, the number of possible stereoisomers should be equal to 4. These isomers are written in Fischer projection as can be seen in Figure 2.6. The pairs of enantiomers are drawn by drawing an imaginary mirror between the two structures, as was shown while studying optical isomers. Figure 2.6. Stereoisomers of 2,3-dibromopentane. First, we draw a configuration I and then its mirror image 2. It is observed that the two structures 1 and 2 are non-superimposable, hence they represent a pair of enantiomers, and both of these will be optically active. If we interchange the bromine and hydrogen at second carbon, i.e., invert the configuration, we get a structure that is different from 1 and 2 and shown as structure 3. Then, we write a structure that is a non-superimposable mirror image of 3, shown as structure 4. As can be seen, structure 4 is also different from 1 and 2. You can say that the compounds represented by structures I4 are all optically active compounds. The compounds represented by structures 1, 2 and 3, 4 are pairs of enantiomers, but what is the isomeric relationship between the compounds represented by I and 3? We can answer this question by observing that I and 3 are stereoisomers and that they do not have a mirror image relationship with each other. Such isomers are called diastereoisomers or diastereomers. Thus, diastereomers can be defined as the pair of stereoisomers which do not have mirror image relationship with each other. The properties of diastereoisomers are listed below. 1. Diastereoisomers may or may not be optically active, and if optically active, these have different values for specific rotation. 2. These possess different physical properties such as MP, solubility, etc. 3. Due to the difference in their physical properties, these may be separated by fractional crystallization, fractional distillation, or by chromatographic techniques. 4. Diastereoisomers differ in some chemical properties also. These may differ in the rate of reaction with the same reagent. Another example that can be looked into is 2-bromo-3-chlorobutane. As can be seen by the structure given in Figure 2.7, it contains two asymmetric carbon atoms. Therefore, the number of possible stereoisomers is 2 square equals 4. These can be represented by 4 Fischer projection structures as given below. Figure 2.7. Enantiomers and diastereoisomers in 2-bromo-3-chlorobutane. You can practice drawing the enantiomers and diastereoisomers of some other molecules. In the following subsection you would study to identify the isomers in case of molecules that have similar stereogenic centers. 2.3.2 mesocompounds. Similar stereogenic centers. We consider molecules with two stereogenic centers which carry an identical set of substituents at each asymmetric carbon atom. Look at the structure of tartaric acid, i.e., 2,3-dihydroxybutyrenidoic acid. You know that it has two chiral centers. How is this structure different from the structures of molecules considered above in subsection 2.3.1? Let us understand it by drawing the various possible stereoisomers for tartaric acid. You can see from Figure 2.8 that of the possible isomers, 1 and 2 represent a pair of enantiomers and 3 and 4 represent another pair of enantiomers. When you look more closely at structures 3 and 4, you can see that these are identical because these are superimposable over each other. Therefore, we can say that the structure 3 is achiral despite containing two stereogenic centers. Figure 2.8. Stereoisomers of tartaric acid. Let us explain the above-mentioned observation. The structure 3 possesses a plane of symmetry which is halfway along the C2-C3 bond, such that CO2H reflects onto CO2H, OH onto OH, and H on to H, as can be observed from the structures 3 and 4 given below. This reveals the opposite configuration of C2 and C3 carbon atoms. You have read in Unit 1 that if a molecule possesses a plane of symmetry, it is not chiral. The same can also be shown for structure, for although these are identical stereoisomers of tartaric acid showing plane of symmetry, thus, we can conclude that structures 1 and 2 are the enantiomers and will show optical activity. The structures I and 3, 2, and 3 are diastereoisomers of each other. As regards optical activity of 3, the effect of C2 cancels the effect of C3 because the stereogenic centers have opposite configuration, so it is optically inactive. As is evident, the rotation due to one half of the molecule is compensated by the rotation of the second half, causing the molecule to become optically inactive. Such compounds were previously called to be internally compensated. It is well known to you that now such compounds are given the prefix meso. The meso compounds are always achiral, i.e., optically inactive even though they have 2 or more stereogenic centers. You would observe that in case of tartaric acid only 3 stereoisomers are possible. Out of these, 2 isomers form a pair of enantiomers and are optically active, whereas the third isomer is meso and inoptically inactive. The compounds with 2 similar stereogenic centers have 3 stereoisomers instead of the expected for stereoisomers. In this subsection you have read that a compound with 2 chiral centers may show optical inactivity due to the cancellation of optical activity of one half of the molecule with that of the other half. You might have studied another situation leading to optical inactivity when a pair of enantiomers is present in equal ratio as a mixture. In the following section let us recall and understand this concept. 2. For racemic modifications, you might have come across reactions where an achiral reactant may end up forming chiral products. If there is absence of a factor that might lead to the formation of a product in major amount, an equimolar mixture of products is formed. For example, the nickel-catalyzed hydrogenation of butanone results in the formation of 2-butanol. As butanone is achiral, the trigonal planar carbonyl group interacts with hydrogen with equal probability to be added from the side, which produces chiral products in equal amounts. As is clear from the reaction given in figure 2.9, mixture of the 2 enantiomers, -2-butanol and -2-butanol is obtained. Figure 2.9, hydrogenation of butanone forming enantiomers of 2-butanol, if both the and enantiomers are present in equal amounts. Each of them rotates the plane of plane polarized light in opposite direction. Such a mixture becomes optically inactive because the rotation caused by one isomer would be exactly cancelled by the other isomer present. Such a mixture is named the racemic mixture or racemate or racemic form. The term used to explain the cause of optical inactivity of racemic mixtures is external compensation, compared to the meso compounds that are optically inactive due to internal compensation. We can say that a racemic mixture causes no net rotation of plane polarized light. It is also written as DL mixture and plus or minus sign is written before the name. For example, a racemic mixture of -2-butanol and -2-butanol can be written as plus or minus -2-butanol or plus or minus CH3CH2CHOHCH3. You have read that an optically active molecule rotates the plane of a plane polarized light when it is passed through its solution. The mixture obtained in above reaction will show no net optical rotation, can be explained as shown in figure 2.10. As can be seen, first a beam of plane polarized light encounters a molecule of one isomer of 2-butanol, a chiral molecule, figure 2.10a. This causes a slight rotation of the plane of polarization, figure 2.10b. This rotation gets cancelled when the light interacts with a molecule of another enantiomer of 2-butanol, figure 2.10c, and no net rotation is observed. Figure 2.10d. If the mixture of 2 isomers is in unequal amounts, a net rotation of the plane of plane polarized light would be observed as shown in figure 2.10e. Figure 2.10, rotation of plane polarized light by a mixture of isomers of 2-butanol. Although several methods are now prevalent for the preparation of enantiomerically pure products, yet large number of such compounds are still obtained by resolution of racemates. Let us first learn how racemates are formed, after which we would focus on their resolution. These are explained in the next subsection. 2.4.1 Formation of racemic mixtures. A racemic mixture is formed by any of the following methods. I. By mixing a pair of enantiomers in equimolar ratio I. The equal number of moles of the enantiomers. If we take 0.5 moles of butan 2-ol and 0.5 moles of butan 2-ol, 1.0 mole of a racemic mixture of butan 2-ol is obtained. The process can be depicted as follows. 2. Production of a chiral center from an achiral compound. One example of this type of reaction has been discussed above and explained in Figure 2.9, which involves the reduction of butanone. Another, similar example can be taken as the catalytic reduction of 2-oxopropanoic acid, pyruvic acid, in which 2 isomers of lactic acid are produced in 50-50 ratio. In this reaction, hydrogen is added across the carbon-oxygen double bond, and this carbon atom now becomes a symmetric carbon atom. Since there is equal probability of addition of hydrogen from any side of the plane of carbonyl group, a mixture of 2 enantiomers is produced in equal ratio, which is a racemic mixture. The reaction is given below. Some more examples involving such reactions are given below. Hydrogenation of alkenes. An achiral alkene on catalytic hydrogenation also gives the mixture of 2 enantiomers, or can be said that a racemic mixture is obtained as shown in the following equation. Synthesis of amino acids. Strecker method, which is used for the synthesis of amino acids, produces a racemic mixture. It involves the reaction of an aldehyde, example acetaldehyde, with ammonia and hydrogen cyanide to give 2-aminopropanenitrile, which on hydrolysis gives plus or minus alanine. 3. Racemization. Racemic mixture is also formed by the process of racemization, which involves the conversion of an optically active compound into a pair of enantiomers by using heat, light, or a chemical reagent. A compound can be racemized under a given set of conditions or by some specific reagent, which depends upon the nature of the compound. For example, racemization may occur by enolization in those compounds which have a carbonyl function attached to a chiral carbon. As can be seen, the treatment of a solution of one isomer, say, sec, butylphenylketones in aqueous ethanol with acid or base, leads to the compound that loses its optical activity, showing that the compound has racemized as given below. This is explained by the formation of enolic structure in the first step. The enol, on reverting back to the keto form, gives equal amounts of the 2 enantiomers. We can also end up with a racemic mixture in a chemical reaction even if the starting material is optically active. For example, substitution reaction of a tertiary alkyl halide which follows SM1 pathway leads to the formation of a racemic mixture. Why? You have studied that in this pathway, the product is formed through a planar intermediate, the carbocation. A carbocation can be attacked by a nucleophile from back as well as front. Many other reactions following SM1 mechanism also produce racemic mixtures. An example is shown in the following reaction. Racemization is not a desired process when we aim to synthesize a particular enantiomer. As you are aware, most of the natural products, foodstuffs, drugs, flavoring agents, perfumes, and other biologically active materials usually show their desirable or beneficial effects in one enantiomeric form only. If in any reaction a racemic mixture is obtained, then it becomes essential to separate the 2 enantiomers. The process involving separation of enantiomers is called resolution. Before discussing the methods of resolution, it is worthwhile to study some important properties of racemic mixtures. These are briefly explained in the following subsection 2.4.2 Properties of racemic mixtures. The enantiomers depict both scalar, only magnitude, and non-scalar, magnitude as well as direction, properties. The scalar properties like melting point, boiling point, solubility in aqueous solvents, density, refractive index, infrared, IR, spectra, Raman spectra, ultraviolet visible spectra, nuclear, magnetic resonance, NMR, non-resonant X-ray diffraction pattern, etc., are found to be the same for enantiomers. Non-scalar properties such as chiroptical properties, interaction with other chiral species and biological activities differ in most of the cases and are dealt in the second block of this course. We will briefly discuss the nature of the racemates in three phases, viz., the gaseous phase, the liquid phase and the solid phase in the following paragraphs. Melting point. There are three types of racemic modifications in crystalline state. The melting point varies depending upon the type. 1. Conglomerates of homochiral species with enantiomers at 50:50 composition have lower melting points than the individual enantiomers. 2. Racemic compounds with each unit crystal having equal numbers of and molecules. The melting point of racemic modification has higher melting point than the individual enantiomers. 3. Pseudoracemates or solid solution forms have the unit crystals in any proportion of and forms. The melting point of the pseudoracemates is almost similar to the individual enantiomers. Crystal shape morphology. The crystals may belong to centrosymmetric or non-centrosymmetric space groups with or without an inversion center between atoms, respectively. The enantiomerically pure compounds form disymmetric crystals or non-centrosymmetric crystals, while the racemic compounds crystallize in centrosymmetric space groups. X-ray diffraction. Studies can differentiate between these two types. Density in solid state. You know that a closer packing of molecules can be expected to exhibit higher density. Therefore, the racemic compounds can be expected to exhibit higher density than the enantiomers. Solubility behavior. The solubility of racemates is twice in comparison to solubility of enantiomers. This generalization is not applicable to all types of racemic modifications and is primarily applicable to neutral organic compounds, i.e. the ones which lack polar groups. Spectroscopy. The IR and NMR spectra of racemic mixtures and that of any single enantiomer are found to be significantly different. You will study about this in the unit on spectroscopy. Chromatographic behavior. Enantiomers show different chromatographic behavior when the adsorbent used is chiral. It is difficult to separate the enantiomers by the use of achiral stationary and mobile phases. However, the predominant enantiomer can be separated from the racemic heterochiral associates under achiral chromatography conditions. In the following section, let us study the methods by which enantiomers can be separated from their racemic mixtures. 2.5 Separation of racemic mixtures. Resolution. The process of separating a racemic mixture into its components, i.e., its enantiomers, viz., and forms, is known as resolution. It is very significant to get the individual enantiomers in pure state, as these have varied characteristic properties and biological reactions. A pair of enantiomers has identical physical and chemical properties, except towards optically active reagents, so their separation is not possible by the usual techniques such as fractional crystallization, fractional distillation, or chromatography. Various methods have been developed for resolution, but the selection of a particular method depends upon the chemical nature of the compound under consideration. 2.5.1 Mechanical separation. This method is applicable for those mixtures only where the enantiomers form different crystals which themselves are enantiomorphous. The crystals of racemic modification contain two types of crystals, which are mirror image of each other. Such crystals can be separated mechanically by using a magnifying lens and a pair of tweezers. This method was introduced by Pasteur, when he separated the crystals of sodium ammonium tartrate, separation of the isomers became possible in this case because the two types of crystals were hemihedric and possessed different orientations. This method is of very limited use and quite cumbersome also. Moreover, all the compounds do not form asymmetric crystals to permit separation mechanically. A more useful variation of mechanical separation is the method of inoculation, originally discovered by Jenner. If a saturated solution of a racemic mixture is carefully inoculated with a pure crystal of one of the enantiomers, the crystal will grow and an appreciable amount of that enantiomer shall be deposited, hence separated from the racemic mixture. For example, sodium ammonium tartrate can be crystallized from a solution of the racemic modification not only by inoculation with a crystal of the salt but also by inoculation with asparagine, H2N-COP2CH, NH2, CO2H. The shape of a crystal depends upon the translational repetition of a basic structural pattern, described as the unit cell that involves a number of forces. Unit cell may contain one or several molecules, the arrangement of which reflects the overall symmetry of the crystal structure. Inclusion complex procedure. An inclusion complex is formed by the treatment of one component called the host, which has a cavity or space in the crystal lattice, with a second compound called the guest. In inclusion complex, the guest fits into the cavity of the host. The guest and host molecules are held by van der Waals forces and there is no covalent bonding. Chiral phenols like 1,1,2-naphthyl, which are optically active, act as good hosts for the separation of racemic mixtures. In such separations, solvents like benzene or hexane are used. The procedure used for separation consists in keeping the racemic mixture, guest, and the host molecule, example 1,1,2-naphthyl, in a solvent, benzene or hexane, for 5 to 10 hours. During this process, crystals of inclusion complex separate out, which are filtered. The mother liquor is used for the isolation of the second isomer. The inclusion complex is formed in the 1:1 or 1:2 host-guest ratio and is recrystallized from the same solvent, benzene or hexane. 2.5.2 Biochemical resolution. Certain bacteria or fungi consume one enantiomer selectively when these grow in the presence of a racemic mixture, while the other remains intact and can be recovered later. The separation by this method is almost quantitative. The enantiomer that is left in solution is isolated by fractional crystallization. For example, a solution of plus or minus tartaric acid is treated with an ordinary mold, Penicillium glaucum, to achieve resolution. The mold selectively utilizes dextrotartaric acid and leaves levotartaric acid. This method has some disadvantages as listed below. The growth of such microorganisms occurs in very dilute solutions, therefore, compound is obtained in small amounts only. One enantiomer is always destroyed. As a result, only one enantiomer is obtained during resolution. A suitable microorganism is also required for the purpose of resolution. It is very difficult to find an appropriate microorganism for a particular substrate. Resolution with enzymes. All enzymes are catalysts. Chiral and stereoselective in their natural aqueous environment. Some enzymes are highly selective whereas others are broadly receptive. For example, formation of one enantiomer of a chiral insect pheromone was achieved by enantioselective hydrolysis of its racemic mixture, Fig.2.12a, by Pseudomonas cepacia lipase, PCL, the enzyme of choice, to produce alcohol, Figure 2.12b. Figure 2.12, resolution of racemic pheromone with PCL. After the reaction is complete, the resolved alcohol is separated from its enantiomeric acetate, Figure 2.12c, which is left unchanged. Similarly, racemic 2-hydroxy-phenylbutanoic acid was reacted with lipase PS, LPS, and vinyl acetate, VA, ethinyl ethanoate, in T-butyl methyl ether, 2-methoxy, 2-methylpropane, to give its acetate in 35% yield and 99% EE. The unreacted alcohol was found to have 99% EE with a configuration, figure 2.13, Fig. 2.13, resolution of substituted butanoic acid with LPS, 2.5.3 chemical methods. These methods involve treatment of the racemic mixture with an appropriate, optically active compound called the resolving agent to form a pair of diastereoisomers. The basis of separation of racemic mixtures in this method is that the diastereoisomers have different physical properties, whereas enantiomers have identical physical properties. If a mixture of enantiomers is converted into a pair of diastereoisomers, these can be separated by using conventional methods such as crystallization, distillation, or chromatography, etc. The pure diastereoisomers are then treated with a suitable reagent to give a pure enantiomer. According to Weiland, 1971, the desirable characteristics of a good resolving agent are stability in use and in storage, ease of preparation, recovery, reuse thus cost-effective, low molecular weight and low toxicity, availability in high enantiomeric purity and availability of both the enantiomers, reasonable solubility. In one of the ways, chemical resolution can be achieved by the formation of diastereoisomeric salts as explained below, formation of diastereoisomeric salts. This method is most suitable for the resolution of carboxylic acids or amines, because they can easily form diastereoisomeric salts. For example, a racemic mixture of acids can form two salts on treatment with an optically active base. The two salts will be diastereoisomers of each other, which can be separated by fractional crystallization. Each of the separated diastereomeric salt will give an enantiomer on treatment with a mineral acid, example, sulfuric acid or hydrochloric acid. The resolution process can be shown with the help of a flow chart given in Figure 2.14. Figure 2.14, flow chart showing resolution by formation of diastereomeric salts, an example of separation of a racemic mixture, acid, using a chiral basis, given in Figure 2.15. One of the asymmetric carbon atoms in the S salt is identical to an asymmetric carbon atom in the S salt, and the other asymmetric carbon atom in the S salt is the mirror image of an asymmetric carbon atom in the S salt. Therefore, the salts are diastereomers, so have different physical properties and can be separated. After separation, they can be converted back to the carboxylic acids by adding a strong acid such as HCl. The chiral base can be separated from the carboxylic acid and used again. Figure 2.15, resolution of a racemic acid by formation of diastereomeric salts. The above method can also be used for the separation of racemic mixture of bases by treating with one enantiomer of a suitable acid. The most commonly used bases for the separation of enantiomers of acids are strychnine, brucine, quinine, ephedrine, menthylamine, and picoline, etc. The acids generally used for the separation of basic compounds are alanine or any amino acid, -10, camphor-sulfonic acid, tartaric acid, malic acid, etc. Structures of some resolving agents are given in Figure 2.16. Figure 2.16, structures of some resolving agents, 2.5.4 chromatographic separation. You are familiar with the principle of chromatographic separation, where the components of a mixture of compounds get separated on the basis of their distribution between the stationary and the mobile phase. If an optically active adsorbent is taken as the stationary phase in the chromatography column, the adsorption for two different enantiomers will be different during elution. The two would get separated after the process is over. Some adsorbents used for this purpose are lactose, quinine, silica gel, etc. The chromatographic method of resolution of racemic mixtures is carried out, generally under three different conditions: direct resolution of the racemic mixture using chiral adsorbent materials. The naturally occurring polysaccharides and their derivatives provide useful chiral stationary phase materials. The microcrystalline triacetylcellulose MCTC forms a versatile column on which a number of compounds, example racemic olefins, biphenyls, ketones, alcohols, esters, acids and salts have been resolved. 2. Direct resolution on an achiral solid phase using a mobile chiral. Liquid phase, many cationic chelated metal complexes, example tris, diamino, metal complex have been resolved on a column of cation exchange cephadex, dextran cross-linked with epichlorohydrin, by elution, with an aqueous solution of tartrate. 3. Direct resolution using an achiral solid stationary phase modified by chiral reagents. An ordinary adsorbent like silica gel is made stereoselective by special treatment with optically active substances, example tartaric acid and camphor. Sulfonic acids which are later removed by elution with solvent. Gas chromatography has also been extensively used for analysis as well as separation of enantiomers working on the above principles. The trifluoroacetyl derivatives of optically active amino acids have been used for gas chromatographic resolution of racemic alcohols via the corresponding esters. Paper chromatography can also affect partial resolution. The paper, cellulose, material itself can act as chiral adsorbent or it may be impregnated with solution of optically active compounds such as camphor sulfonic acids. 2.5.5 Kinetic methods. This method is based on the principle that sometimes the rate of reaction of enantiomers with a particular reagent is different, i.e., Kr is not equal to Ks. This is possible because the activation energy of the diastereomeric transition states in the reaction of the racemate with a chiral reagent are different, and so the two enantiomers react at different rates. For example, menthol reacts with mandelic acid at a faster rate than that with isomer. If plus or minus mandelic acid is esterified with insufficient quantity of menthol chiral alcohol, the resulting mixture will have menthol mandellate formed at a faster rate and in larger amounts. The unreacted mandelic acid will be rich in the enantiomer. These are separated and repetition of the process may lead to almost full separation. Mandelic acid can be obtained by the hydrolysis of the ester obtained. You have learnt that it is important to separate a desired isomer from a mixture of isomers because of a specific utility of one over the other. When separated from a racemic mixture, it is essential to check the extent of purity of the isolated isomer. In the following section we will discuss what are the criteria of purity of the isolated isomers. 2.6 Criteria of optical purity. You know that racemic mixture has a composition of 50:50 enantiomers of both the types. The composition of non-racemic mixture has enantiomer composition different from 50:50. If only one enantiomer is present, it may be called enantiopure or enantiomerically pure. The term enantiomeric excess, E, is defined in simple percentage terms as follows. Enantiomer IC excess equals excess of a single enantiomer upon entire mixture into 100%. When we consider the number of moles of the enantiomers involved, the above expression can be modified as follows. Enantiomeric excess equals moles of one enantiomer minus moles of other enantiomer upon total moles of both enantiomers into 100. The terms in the numerator arise because what the polarimeter registers is a measure of the difference in population of the enantiomers in a sample. An enantiomeric excess of 50% signifies that the sample contains 75% of the enantiomer with, say, or D, optical rotation, and 25% of, or L, that is 50% of, a 1,1 mixture and 50% of the, or D, enantiomer. The enantiomeric excess can be calculated from optical rotations by the following formula. Enantiomeric excess equals observed specific rotation upon specific rotation of the pure enantiomers into 100. The enantiomeric purity is expressed as optical purity also and can be given as follows. Optical purity or OP equals alpha OBS upon alpha max into 100%. A crystalline enantiomer is often considered optically pure when its melting point and rotation are unchanged by further crystallization. However, this criteria of calculating or getting an idea of the optical purity fails when the racemic modification forms a solid solution, since in that case even a partially resolved enantiomer may not change in either rotation or melting point by further recrystallization. Apart from sample purity, the optical rotation is affected by solvent polarity, moisture content in the solvent, temperature, wavelength employed, and the possibility of human error. Thus the determination of enantiomer composition by use of equation given above can give a rough estimate of the enantiomer composition in a solution of a chemically, not enantiomerically, pure compound. The values of optical purity and enantiomeric excess are identical. If the solution does not contain any other compound except for the solvent, and the specific rotation of the pure enantiomer is known, the enantiomeric excess may be determined by measuring the optical rotation of a solution of a two-enantiomer mixture. In order for the optical purity and the enantiomeric excess to be calculated, the specific rotation of the pure enantiomer must first be noted. Therefore, a mixture showing a specific rotation of one of the enantiomers is said to have an enantiomeric excess of 100%. For example, an enantiomerically pure sample of S-2-butanol shows a specific rotation of 13.52. 25D. On the other hand, a sample of S-2-butanol that contains less than an equimolar amount of R-2-butanol will show a specific rotation that is less than 13.52 but greater than 0. Such a sample is said to have an enantiomeric excess less than 100%. If a mixture of the enantiomers of 2-butanol shows a specific rotation of 6.76, the enantiomeric excess of the S-2-butanol can be calculated as enantiomeric excess equals 6.76 upon 13.52 into 100 is equal to 50%. On the basis of the above calculations, it can be said that of the total mixture, 50% consists of racemic form, which contains equal number of the two enantiomers. So, half of 50%, or 25%, is the enantiomers and 25% is the enantiomer. The remaining 50% of the mixture is also the enantiomer, so the mixture is 75% enantiomer and 25% enantiomer. 2.7 molecules with 3 or more chiral centers. You have learnt the general formula that is applied to find out the number of stereoisomers in a chiral molecule. By using the formula 2N, we can say that a compound with 3 stereocenters, N equals 3, can have 8 stereoisomers. As the number of stereocenters in a molecule increases, the stereochemical situation might become more complex. Let us understand the case of molecules that have 3 stereocenters by taking 3-bromo-4-chloro-2-pentanol as an example. We can draw 8 possible configurations, 1 to 8, for this compound, as shown in figure 2.17. These are drawn in such a way that for one structure its mirror image is shown next. For example 2 is the mirror image of I, where a hypothetical mirror is shown in between. Similarly, other pairs are 3 and 4, V and 6, 7 and 8. Since none of the mirror image is superimposable, so there are 4 pairs of enantiomers and all the 8 isomers will be optically active. Figure 2.17, stereoisomers of 3-bromo-4-chloro-2-pentanol. You will learn another term here that is related to the absolute configuration of molecules with 3 stereocenters. The term is called pseudoasymmetry, about which you will study in the following subsection. 2.7.1 Pseudoasymmetry. Certain molecules may contain tetrahedral carbon atom that is joined to two constitutionally identical chiral groups and two other different achiral groups. The chiral groups may or may not have the same absolute configuration. Let us take the example of trihydroxyglutaric acid. The possible stereoisomers of this molecule are given in figure 2.18, 1-8. It has three stereocenters as depicted by the numbers 2, 3, and 4. Figure 2.18, stereoisomers of 2, 3, 4, trihydroxyglutaric acid. If we look at these structures carefully, it can be seen that structures 1 and 2 are identical, as these can be interconverted by a 180 degrees rotation in the plane of the paper, and that they represent a mesostructure. The central carbon atom, C3, in structure 1 or 2 is a stereocenter, as 4 different groups are attached to it. Although the two groups vertically attached to C3 as drawn contain the same functional groups, these have opposite absolute configurations which are responsible to make C3 a stereocenter. The stereocenter C3 in structure I is the pseudoasymmetric center. The existence of a pseudoasymmetric center in a molecule can be called pseudoasymmetry. The RS nomenclature system can be applied to pseudoasymmetric centers through lowercase letters r and s are used to represent their configuration. Same is true for the pair represented by structures 7 and 8. These do not represent a chiral species because these are also superimposable on their mirror images. As in the case of the meso compound represented by structure I, the central carbon atom, C3 in compound 7 or 8 is also a pseudoasymmetric center. Structures 3 and 4 represent a pair of enantiomers, as these differ in the absolute configuration at each of their stereocenters. In these two compounds, the central carbon atom C3 is not a stereocenter, as the two groups vertically attached to it are identical both in the functionality contained and in their stereochemistry. Thus, in this pair of stereoisomers, C3 has only 3 different groups attached to it and the compounds contain only 2 stereocenters. Structures V and 6 do not represent new species, as these can be superimposed on structures 3 and 4 respectively by a 180 degrees rotation about a horizontal axis through C3. Thus, there are just 4 stereoisomers of trihydroxyglutaric acid, a pair of enantiomers represented by structures 3 and 4, and 2 mesoisomers represented by structures I, or 2, and 7, or 8. The mesoforms are diastereomers of each other and of the pair of enantiomers. Hence, due to the symmetrical nature of trihydroxyglutaric acid, there are considerably fewer than the maximum 8 possible stereoisomers. It exists in 4 stereoisomeric forms, 2 of which are optically active, 3 and 4, while the other 2, I and 7, are optically inactive because they are mesoforms. In all, it contains 2 asymmetric and 1 pseudoasymmetric carbon atoms. Let us again look into the molecule of trihydroxyglutaric acid to understand it from the point of view of configuration at different stereocenters. The possible stereoisomers of this molecule are given in figure 2.18, 1-8. It has 3 stereocenters as depicted by the numbers 2, 3, and 4. Table 2.1 shows the absolute configuration at each stereocenter for each of the 8 structures. When odd number of chiral centers is present in constitutionally symmetric molecules, the total number of stereoisomers possible is given by 2n1. Such molecules produce chiral and meso-achiral stereoisomers. Table 2.1, absolute configurations of 2, 3, 4 trihydroxyglutaric acid structures. I equals not a stereocenter since 2 of the groups are identical. S equals pseudoasymmetric center. If we analyze the structures and the absolute configuration given in the above table, it can be seen that structures 1 and 2 are identical. They can be interconverted by 180 degrees rotation in the plane of the paper, and that they represent a mesostructure. In general, a molecule can have one pseudoisomeric center only when the number of constitutionally alike chiral centers is n1, and the value of n is even and the minimum value is 4. For example, 2, 3, for trihydroxyglutaric acids can have a pseudoisomeric center, but 2, 3, for 5, tetrahydroxyadipic acid has no possibility of having a pseudoisomeric center. 2.8 Summary. Let us summarize the key concepts studied in this unit. A carbon atom with 4 different groups attached to it becomes chiral and hence called a chiral center and generates chirality in the molecule. This generates stereoisomerism in the molecule. The chirality in the case of molecules with 1, 2, and 3 chiral centers has been discussed in this unit. The molecules like methane and bromomethane have their mirror images superimposable upon each other, therefore contain an achiral carbon and do not show optical activity. While the molecules with 1 chiral center like bromochlorofluoromethane has a non-superimposable mirror image and shows optical activity. The isomers obtained are called the enantiomers. Some other molecules belonging to this category are lactic acid, glyceraldehyde, alanine, etc. The stereoisomers with 2 chiral centers are not only in the form of enantiomers as observed in molecules with 1 chiral center but also form another type of stereoisomers called the diastereoisomers or diastereomers. The diastereoisomers can be defined as the pair of stereoisomers which do not have mirror image relationship with each other. The stereoisomers with more than 1 chiral center broadly fall into 2 categories. These are isomers with dissimilar stereogenic centers and isomers with similar stereogenic centers. The number of stereoisomers is calculated by the formula 2n, where n is the number of chiral centers. For example, 2,3-dibromopentane molecule contains 2 asymmetric carbon atoms. Therefore, the number of possible stereoisomers should be equal to 4. The enantiomers and diastereomers of the molecule 2,3-dibromopentane can be drawn in Fischer projection. Another molecule of this type considered is 2-bromo,3-chlorobutane. Tartaric acid is the example of a molecule having similar stereogenic centers. One of the isomers here is prefixed as meso, which is optically inactive as the rotation of one half of the molecule is compensated by the rotation of the second half. In some cases the and enantiomers are present in equal amounts in a mixture. As a result, there would be no net rotation of the plane of polarized light. Such a mixture becomes optically inactive because the rotation caused by one isomer would be exactly cancelled by the other isomer present. Such a mixture is named the racemic mixture or racemate or racemic form. There are a number of ways of formation of a racemic mixture. Example, mixing a pair of enantiomers, racemization, hydrogenation of alkenes, etc. The process of separating a racemic mixture into its components, i.e., its enantiomers, vis, and forms, is known as resolution. The methods employed here are mechanical separation, biochemical resolution, resolution with enzymes, chemical methods, chromatographic separation, and kinetic methods. The extent of purity of the isolated isomer from a racemic mixture can be found out by calculating the enantiomeric excess. The enantiomeric excess of 50% means that 50% of the mixture consists of the enantiomer, the excess, and the other 50% consists of the racemic form. Since for the 50% that is racemic the optical rotations cancel one another, only the 50% of the mixture that consists of the enantiomer contributes to the observed optical rotation. The observed rotation is, therefore, 50%, or 1/2, of what it would have been if the mixture had consisted only of the enantiomer. As long as the compound is chemically pure, enantiomeric excess and optical purity will be the same. A compound with 3 stereocenters, n equals 3, can have 8 stereoisomers. As the number of stereocenters in a molecule increases, the stereochemical situation might become more complex. For example, 3-bromo, 4-chloro, 2-pentanol can be depicted by 8 isomers. Certain molecules may contain tetrahedral carbon atom that is joined to 2 constitutionally identical chiral groups and 2 other different achiral groups. The chiral groups may or may not have the same absolute configuration, example, trihydroxyglutaric acid. In such cases, the number of isomers would be less than the expected 8 isomers and are considered to have a pseudo-asymmetric center. Thank you. Subscribe to our channel for more updates, and we will see you with the next chapter.